Okay, hi everyone, this is Boniface, the Radical Tutor. In this video, we are going to prove the Cauchy-SCWARTZ inequality. So we are going to state and prove the Cauchy-SCWARTZ inequality. Now, how do we state the Cauchy-SCWARTZ inequality and how do we prove it? So we are going to start by stating it. All right. So we are going to say the Cauchy-SCWARTZ inequality states that for any vectors u and v in an inner product space, which in this case can be v, capital V, comma, the inner product space of u, comma v is less or equal to inner product space of u times inner product space of v. So this is how the Cauchy-SCWARTZ inequality states. Now, if this is what the Cauchy-SCWARTZ inequality states, how can we prove that v is equal to that? So this is what we are going to do in this video. Now, doing that, what we are going to do is we are going to start by creating some assumptions. So you can say, let us have two inner product or two inner vectors multiplying in a vector space, which are, we can have u plus tv, which can multiply with u plus tv in an inner product space. So we have these two vectors that are going to multiply in an inner product space, and therefore we are going to say this is greater or equal to 0. So remember, when we are proving something, this was proved by Cauchy-SCWARTZ in early 1830s. So what we are going to do is we are going to follow what he already did or what he already proved. So that's what we are doing. So now from here, what we are going to do is we are multiplying this and that. So we multiply this and that. What are we going to get? So you multiply u times u, which is going to be inner product space of u times inner product space of u, and then you multiply u times tv. You are going to have plus u, that is inner product space of u times inner product space of v times that t there. I've multiplied this and that. So we are done with this and what is in that bracket. Now we are going to this and that as well. So we say plus, we multiply tv times u, we are going to get inner product space of u, inner product space of v, but there is a t here, so we are going to have that t. And then from here, what we are going to do is we also have tv times tv, which is going to be plus inner product space of v times inner product space of v, but we have the t and the t that can also multiply to get the t squared, so we can have t squared here. Then from that, what we are going to do is we can say inner product space of u times inner product space of u, you are going to get inner product space of u squared, and then plus we have inner product space of u vt plus inner product space of u vt. The answer that we are going to get is inner product space, or we can say we add the 2, this and that, we are going to get a 2 inner product space of u, inner product space of v, but with a t, so with a t there. Okay, then plus the final one, which is inner product space of v times inner product space of v, we are going to get inner product space of v squared, and then we have the t squared as well, like that. So from here, what we are going to do is very simple. You are going to say the way this function that we've obtained is looking like a quadratic equation. Actually, it is in the form of quadratic equation. So what you can do is to say this is, remember, quadratic equation is written in the form ax squared plus bx plus c is equal to 0. Okay, don't forget that these are greater or equal to 0, greater or equal to 0, like that. So this function that we've obtained is in the form of quadratic form. So if it is in the form of quadratic form, what we can do is you can say let this to be our a. So we are going to let this to be our a, this to be our B, and this to be our C. So after making this A, B, and C, what you can do is to now get what we call as discriminant. So how do you get discriminant? So discriminant is used to identify or predict the answers for any quadratic equation that you have. So that is the function of discriminant. So we're going to get discriminant, and discriminant is given as b squared minus 4ac. So this is the formula that is used to get discriminant. Now, this guy believed that for this quadratic equation obtained to have proper solutions or real solutions, he said the discriminant should no longer be greater or equal to 0, but it should be less or equal to 0. So we are going to say the discriminant should be less or equal to 0. And then we can make b squared the subject by saying b squared is less or equal to, we take the 4ac the other side, we are going to have 4 positive 4ac. Now, after I've done that, what we're going to do is to replace, because we know that our b in this case is the 2 inner product space of u, v, t, and our a is this is our c. So we're going to replace the values of a, b, and c in the discriminant. That's what we are going to do. So we're going to say, let me do it from here. So we're going to say where there is b squared, so where there is b squared, we are going to have, so where there is b squared, we are going to have this one here, which is the 2u vt. Now in this case, the b is only this excluding the 2, so we are not putting the t. All right, so we have 2 inner product space of u, inner product space of v. Okay, we'll put where there is b, and then we need to square this, which is less or equal to 4 open, where there is a, we are putting what? Where there is a, we are putting this, which is the inner product space of v squared. So we put inner product space of v squared. All right, and then times c. So what is our c? Our c is this one here, which is inner product space of u squared. So we put also inner product space of u squared, like that. So now after I've done this, what we are going to do is we square this one here. So when we square 2 squared is 4, and then inner product space of u v squared is going to be, so 4 inner product space of u v squared, this can be put in one bracket so that we can have an inner product space of u, or I can just say inner product space of u comma v, like that, and then square outside. Then this is less or equal to, so it is less or equal to 4 inner product space of v squared, inner product space of u squared. So inner product space of v squared and inner product space of u squared, like that. All right, so what we can do is, of course, I've left the 4 here. I don't know if you've seen it, this 4 here, don't forget to put it, so we need to put that 4 here. So this 4 is very, very important as well. Okay, so you can see that here, this side we have a 4, that other side also we have a 4, and therefore what we can do is to divide them out. So you can divide this and that so that they can go. So if those disappears, then what we are going to remain with here is the inner product space of u comma v squared, which is less or equal to inner product space of v squared, so which can also be written as inner product space of u squared and inner product space of v squared. So we have this which is remaining now. Okay, now since you've seen that we have a square here, you can remove the square by introducing a square root. So you can introduce a square root this side, also introducing a square root that side. So if you have to introduce a square root this side and that side, what is going to happen is that this is going to cancel with the square root, and then this 2 will cancel with the square root, that 2 also will cancel with the square root, and therefore you are going to remain with the inner product space of u comma v. Now here you've introduced a square root, meaning that we should put these in absolute values to show that the answer that we will get should be an answer that will not have any sign. Okay, that is not going to be written with regard to any sign. So we need to introduce the absolute values, and then this is less or equal to. Here we are only remaining with what? Inner product space of U and inner product space of V. So this is what we've gotten as our final answer, and then we say hence what? Hence proved. So that's how we can prove. You can see that what we are proving is here, and this is what we've exactly gotten. So that's how we can prove the Cauchy-Schwartz inequality. So you can say hence proved. Alright, so this is where we can end today with this video. Don't forget to follow my Facebook page, and please go and subscribe to my YouTube channel for more videos of this kind. See you next time.